Sound check one. Okay, good morning. We're going to go ahead and get started since the sound check was good. Remember that you can type questions into the chat bar, and don't worry about interrupting, although there may be a delay between when I read your question and respond, so hang in there. We'll get to it. In the meantime, I'm going to go ahead and proceed with Chapter 4, Section 1. We're going to talk about graphs of functions and what the first derivative tells us about those graphs. The objectives that we're going to focus on are increasing, where the functions are increasing and decreasing, where they have what we call local extrema, which also we call local maxima and minima. Both of those are types of extrema. We're going to talk about something called the first derivative test and some applications. So let's start with this graph here of f of x equals x cubed minus 3x. And try to zoom in a little bit. Okay, so here's our graph. I am gonna adjust this a little bit. It looks a little off to me, but what it's supposed to be is that right about here is where -1 is. This is the point -1, comma 2, and here at the bottom is the point 1, comma -2. And we're going to answer questions about the graph. And the first one is, on what intervals, and when we say on what intervals, we're always referring to intervals of x values. On what intervals is f of x, which is the y value, increasing? So you read a graph from left to right, just like you read a book. So when I say increasing, and I'm talking about y values, we're looking for where the graph is going up from left to right. Okay, so just let's come over to the graph here, and if you follow along the graph, you see how it starts out by going upward from left to right, then it switches to going downward for a little while, still going down, 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 and then it turns around and goes back up, up, up. So when we say on what intervals is f of x increasing, we're going to start back here at negative infinity, look at each interval of values, and then end at positive infinity to make sure we cover everything. So from negative infinity up until the x value -1, the graph was going up, right? At the x value of -1, something happens, it turns around. But up until that point, it was going upward. So one interval on which f is increasing would be negative infinity to -1. All right, then at -1, it turns around, it's going down, down, down until the x value 1. At the x value 1, it turns around and starts to go back upward again, so it's increasing from 1 to infinity. In part B, they're asking where it's decreasing. Well, we already noticed that between -1 and 1, it was decreasing, so that's the interval we're going to list here, -1 to 1. Sometimes I will ask you not on what intervals is f of x increasing, but I'll just say where is f of x increasing. Where always refers to x values. I always say think of the x values like mile markers on a highway. So if I say where, I'm talking about the x values. If I say what, I'm talking about the height or elevation. Okay. Next question about this graph. Do you see any maximum or minimum points? Now, when we say maximum or minimum, we're talking, unless I specify otherwise, about what's called a local maximum or a local minimum. A local maximum is a point where the graph turns around. It starts out going up, but then it turns around, leaving a little peak. This is a local max is a peak, whereas a local minimum is a valley, where the graph goes downward and then turns around and starts to go up again. So do we see any peaks or valleys in this graph? And where do they occur? Now remember, where again means x values. Can anyone type into the chat bar an x value where we have a peak or a valley? Okay, so I see that you said the point -1, 2 is where a peak occurs, and you're correct. What we would say is when we ask where, though, we're only looking for the x values. If I asked what was the maximum or minimum, that would be asking for the y values. So you're going to say it occurs at x equals -1. Okay, that is a max or a local max. Where do we have a local minimum? Karina asked, is it supposed to cross the x-axis? The graph does cross the x-axis in a couple of places, but we're not concerned about those right now. We're looking for where the graph has a local maximum or minimum, a peak or a valley. Very good. Joshua, we have a local minimum at x equals 1. Okay, so we only list the x value, not both coordinates. We would say the local min occurs at x equals 1. If I asked you what is the local minimum, you would say that the local minimum is y equals -2. And if I asked you what is the local maximum, the max is y equals 2. Okay? All right, now the next thing we're going to do is we're going to use calculus to find where this function has horizontal tangent lines, and then we're going to look at the graph and see why that happens. So I'm going to give myself a little more space here. Remember, the function was x cubed minus 3x, so let's write that down. F of x equals x cubed minus 3x. How do we find horizontal tangent lines? So remember, tangent lines are the slope of the tangent line is the value of the derivative at the given point. And a horizontal tangent line has a slope of 0. So we're looking for exactly where f prime of x, the slope, is equal to 0. So let's go ahead and find f prime of x. We want to know the x values for which f prime of x equals 0. So first we have to find f prime of x. The derivative of x cubed is 3x squared. The derivative of -3x is just -3. So we want to know where is that equal to 0. So we have an equation to solve. 0 equals 3x squared minus 3. So this is a quadratic equation because we have a power of 2, but it's one that only has 2 terms. So let's go ahead and try to factor this. Factoring out of 3, we get x squared minus 1. X squared minus 1 is a difference of 2 squares. So this could factor into x minus 1, x plus 1. You could also have used the square root property on this problem, but either way you should get the same result. Using factoring, though, we use the zero factor property, so we say either the factor of 3 is 0, or x minus 1 is 0, or x plus 1 is 0. Obviously it's impossible for 3 to equal 0, so we can throw that out. So either x equals 1 or x equals -1. So those were places where our graph would have a horizontal tangent line. Let's go draw those horizontal tangent lines in. Remember, x equals 1 and x equals -1. Okay, so here was the point -1, 2, and it bothers me that that doesn't line up. Okay, and we said at x equals -1, we have a horizontal tangent line. Okay, the slope of the function is 0 at that point, and down at x equals 1 as well. So you can see that these horizontal tangent lines, the place where the slope or the derivative is equal to 0, occur exactly at those local extrema, the local maximum and the local minimum. You can also observe that those local max and mins and those horizontal tangent lines occur where the graph turns around. In other words, where it changes from increasing to decreasing and where it changes from decreasing to increasing. So this is going to be important to us today. Sometimes we'll be given the graph, and sometimes we don't have the graph, so we'll have to use calculus to figure out where these things are happening. Some terminology that we'll need to use is what we mean by critical values. So as we just saw in the previous example, where the derivative equals 0 is important because we have horizontal tangent lines there, and we have the situation where the graph could potentially turn around. So anywhere where our first derivative is equal to 0 is considered a critical value. But strange things can also happen, and important things can happen where the derivative is undefined, does not exist, I should say. All right, so Critical values are defined to be critical values of the function f are those x values in the domain of f. That's important because the x has to make sense when you plug it into f, or else it doesn't make sense to talk about its derivative there. Where the derivative is equal to 0 and where the derivative does not exist. And when the derivative is equal to 0, you often will have horizontal tangent lines. You'll always have a horizontal tangent line. And when the numerator of the fraction equals 0, if you're working with a function that has a fraction, you're going to be checking where the numerator is 0 to see where the derivative is 0. And then, well, I said that poorly. When you have a derivative that is a fraction, finding where it equals 0 means setting the numerator equal to 0. So that's important to remember. And then where the derivative doesn't exist is where you have derivatives where the denominator is 0, so you have division by 0. Okay, now the derivative also won't exist if you have negatives under a square root, or in the case of the natural log, remember you can only plug positive numbers into the natural log. So if you have a 0 or a negative plugged into the natural log, that's going to be undefined as well, and the derivative wouldn't work there. Okay, so, but the key thing is critical values occur where the derivative is 0 or undefined. Okay, so what are the critical values of the function x cubed minus 3x, the one that we worked with above, and how do you know? Well, the critical values that we observed when we found f prime of x equals 0, when we found that happens at x equals 1 and x equals negative 1, or another way of saying that is f prime of 1 is 0 and f prime of negative 1 is also 0, that is exactly where you have critical values. Now remember, f prime of x was actually 3x squared minus 3. This is never undefined. It doesn't have any fraction, it doesn't have a square root, it doesn't have a natural log. It's never undefined, so there's not going to be any critical values due to the derivative being undefined. Only critical values due to the derivative equaling 0 for this particular function. Okay, the next thing we're going to look at is this graph, and we're going to find where we have certain characteristics. So first of all, we're going to start by talking about local maxima. Maxima, by the way, is plural, and maximum is singular. Okay, but we're just talking about the same thing. And so a local maximum occurs when, and by the way, I'm always going to be talking about x in the domain of the function f. So if f is undefined at a particular x value, we're not going to include it in our discussion here. So a local maximum occurs at x values where the function changes from increasing to decreasing. And instead of saying the function, I'm going to just say where f, this function's called f in this case, where f changes from increasing to decreasing. Okay, in other words, a local maximum is a hill, right? It looks like this. So where do we have a hill or a peak? A peak is probably a better way of putting it because it might be a nice rounded hill or it might be pointy. Okay, so where do we have local maxima? So looking across at C1, C2, C3, C4, C5, C6, and C7, these are all of your x values. Okay. Where do we have a local maxima? Well, for example, look at C3. At C3, we have a peak. Now, it doesn't ask where the local maxima occur, it asks what they are. So when it asks what the local maxima actually are, we're talking about y values. Or in other words, I could say that this point here, C3, has a y value of f of C3. So I'm going to say that f of C3 is one of the local maxima. All right, now what's another one? Does anyone see another one where we have a peak? C1, C2, C3, C4, C5, C6, and C7 are the ones we're looking at. Does anyone see one of those besides C3, which is a peak? C6, very good. Now C6 looks quite a bit different than C3 because it doesn't nice and softly round off at the top. It has a sharp point, but it still is what's considered a local maximum. We change from increasing on the left to decreasing on the right. So the local maximum is f of C6, whatever that y value is there. Okay, now a local minimum is defined to be occur at x values where f changes from decreasing on the left to increasing. In other words, decreasing to increasing is describing a valley. So a local minimum occurs at x values where the function f changes from decreasing to increasing. Again, we always read a graph from left to right. So decreasing on the left to increasing on the right. But just think of it as a valley. So where do we have a valley? Good, Karina. C2 is a valley, and also C4. So if I ask you what are the local minima, I'm asking you for the y values. If I asked you where are they, I would say C2 and C4, but since I ask you what are they, I'm going to say f of C2 and f of C4. Now, when you see the word local or the phrase local extremum, this is just not specifying if we're talking about a hill or a valley. It's either one. So when it asks you for local extrema, that's going to occur at any x value where f changes from either increasing to decreasing or decreasing to increasing. Okay, either way, a peak or a valley. So the local extrema for this function are all the ones we've already listed. F of C2, F of C3, F of C4, and F of C6. So it's just a lumping together max and min. Okay, now notice how important it was in identifying the max and the mins, whether the function was increasing or decreasing. Increasing means going up from left to right. Decreasing means going down from left to right. So we're first asked here to find the intervals, which refers to x values, on which f is increasing. So I'm going to scroll back up to my graph. Okay, let's go ahead and highlight where we're going up from left to right. So from left to right, we're going down, down, down until we reach C2. And then we start to go up, 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 up. Okay, then we turn around and go back down again. And then at C4, we start going up, 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 up. We kind of flatten out at C3, C5 rather. And then we continue going up, 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 up until C6. So what we see here is that we have 3 intervals on which the graph is increasing. It's increasing from C2 to C3, it's increasing from C4 to C5, and again from C5 to C6. So let's write that down. The function is increasing from C2 to C3, from C4 to C5, and then again from C5 to C6. If on a test you were to put just one interval from C4 to C6, I would be okay with that. I'm not sure how my math lab would respond. Okay, this function is decreasing on which intervals. So again, whenever we ask you on which intervals, we're talking about x values. And it's going to be decreasing pretty much everywhere else, right? So we are going to have an interval from negative infinity to C1, from C1 to C2, from C3 to C4, from C6 to C7, and C7 to positive infinity. In each one of those cases, the graph is going downward. It's decreasing, decreasing, decreasing from left to right. Okay, so let's fill in those intervals. So we have the interval from negative infinity to C2. We have the interval from C3 to C4. Oh, I'm sorry. I prefer to say the interval from negative infinity to C1 and then C1 to C2 rather than lump them together. But again, I'll be flexible on that on the test. And then from C3 to C4 and from C6 to C7 and from C7 to infinity. Okay. Next question. At what locations does f prime of x equal 0? Where is the slope equal to 0? That's the same as asking where do we have a horizontal tangent line. All right, so let's look back at our graph. And where do we see horizontal tangent lines? And where is referring to x values, so you're just going to say C1, C2, C3, C4, C5, C6, C7, whichever of those you see. Does anyone want to type into the chat bar an example of an x value where we have a horizontal tangent line? Good. C1, C2, C3, and C5. Good, Karina. Okay. So these horizontal tangent lines are drawn in for us, which is nice. but it's going to happen anywhere that the graph kind of flattens out. And so we see C1, C2, C3, C5. Okay. At what locations does the derivative of f not exist? All right. So in this case, the function exists for all x values, but the derivative doesn't exist if you have a sharp point and or an asymptote, but that would, again, a vertical asymptote would mean the function didn't exist. So we don't have any of those. These dotted lines, by the way, are not supposed to be asymptotes. They're just showing you where the x value matches up with the graph. So, okay, so where do we have sharp points that would essentially result in a vertical tangent line? Well, what I mean by sharp point would be something like C4. You see how C4 is getting steeper and steeper and steeper as we draw tangent lines coming in from the left, and the same thing from the right. So you're essentially going to get a vertical tangent line which has a slope which is undefined. Okay, you can tell that's going to happen whenever you have a sharp point. Here's another one at C6, and at C7 it might not at first glance look like a sharp point, but it is. And although it's not resulting in a vertical tangent line, what's happening is coming in from the left, you're going to get one tangent line, whereas coming in from the right, you're going to get another tangent line. And remember, derivatives are limits, and if the limit from the left doesn't equal the limit from the right, then the overall limit is undefined. So f prime of x, or f prime of C7, I should say, is undefined. So we have C4, C6, and C7, where we have the derivative does not exist. C4, C6, and C7. Okay, now it asks, what do C1, C5, and C7 have in common? So let's look at the graph and look at what's happening at C1, C5, and C7. All right, so C1 was here, C5 is here, and C7 is here. Okay, so what stands out to me is that at each one of these points, we have a situation where the graph started to was decreasing up until and then decreasing again, or increasing up until that point and then increasing again. Same thing over here, decreasing and then decreasing again. But that doesn't mean that something, even though it didn't change from increasing to decreasing and it doesn't have a local max or min, it doesn't mean that there isn't something special happening at that point. What is happening at that point is that we have a critical value, because here the derivative is f prime of C1 is 0. We have a horizontal tangent line. Here we have f prime of C5 equals 0. And here we have f prime of C7 equals undefined. So although we do have a derivative that is either 0 or undefined, we don't actually have a max or a min. So let's write that down. So we have the derivative is 0 or undefined. But we have no local extrema. Okay, so this is important to understand. We're not guaranteed to have a local max or a local min at every single place where the derivative is 0 or undefined. But if you have a local max or local min, then it must have been that the derivative was 0 or undefined. The other way around is true. So at what locations is f prime of x less than 0? Well, whenever you see less than 0, I want you to think of the word negative. So at what locations is f prime negative? Well, what does f prime represent? It represents the slope of the function. And what is a negative slope? A negative slope looks like this. It's going downward from left to right. This is a negative slope. So this is exactly the same as asking where the function f is decreasing, because that's what a negative slope means. So really, we've already answered that question. Where was the function decreasing? Negative infinity to C1, C1 to C2, C3 to C4, C6 to C7, C7 to infinity. So we're just going to write the same answers down. Negative infinity to C1, C1 to C2, C3 to C4, C6 to C7, and C7 to infinity. Okay, at what locations does f prime of x, the slope, turn out to be greater than 0? Whenever you see greater than 0, I want you to think positive. Okay, so positive means going upward from left to right. Positive slope means that f is increasing. So we also answered that as well. Remember, f was increasing from C2 to C3 and from C4 to C5 and from C5 to C6. Okay, so there's two different ways to ask the same question. You can ask where is the function increasing, or you can ask where is the first derivative positive. All right, before I move on to the next page, are there any questions? Okay, so moving on. Okay, so to tell where we have extrema, which are just peaks and valleys, is easy when you have a graph. But a lot of times we don't have a graph and we have to use calculus to locate these extrema. And so we use this theorem that says if f is continuous on the interval from a to b, and c is any number in AB, and f of c is a local extrema, then either f prime of c is 0 or f prime of c does not exist. In other words, the only possible places for local extrema to occur is where the derivative is 0 or does not exist. And remember, the derivative is 0 or does not exist is another way of saying that we're at a critical value. That's all a critical value is. So local extrema only occur at critical values. All right. Before we actually analyze a function from scratch, we need to get used to the idea of using something called sign charts. You may have used sign charts to solve inequalities, quadratic and rational inequalities in college algebra. And we're going to use them again here, so we need to get used to them. So all that a sign chart is a number line, like at the x-axis, where on the bottom of the number line we have x values, and then on the top of the number line we have positive and negative symbols to tell us for which x values the function we're analyzing is positive or negative. And we're going to often be looking for analyzing the first derivative, which is the slope of the function f, because when the slope of the first derivative is negative, our function f will be decreasing. And when the slope of our when our first derivative is positive, that indicates it's the slope of our function f, so that tells us that positive slope means f is increasing. So we'll be able to use sign charts and analyze them to tell us what the shape of the graph looks like, but moreover, where we can find those extrema. So as an example here, we have a sign chart for f prime. We have the x values, let's just focus on the x value c here. To the left of the x value c, we have negative symbols. To the right of the x value c, we have positive symbols. So that tells us if the derivative, the slope, changes from negative to positive, the function f changes from decreasing to increasing. So there are several possibilities. Sometimes you'll have a 0 written in here to indicate that the derivative at c is 0. So if f prime of c happens to be 0, then a change from decreasing to increasing going through a slope of 0 is one of these that looks like a nice little rounded valley. So we're decreasing, and then we have a slope of 0, horizontal tangent line will occur there, and then we're increasing again. So that's one possibility for the graph when f prime of c is 0. What if f prime of c is not 0? What if it's undefined? So if you have a u here instead to indicate that the derivative is undefined at that point, f prime of c equals undefined, then we're not going to have a nice horizontal tangent line. So that could happen for a number of reasons. One, it could be that the graph comes to a sharp point. So it goes downward and then goes back upward with a sharp point. So the slope coming in from the left doesn't equal the slope from the right. So that's one possibility. You still, though, have a local minimum. Now, it's also possible that the reason that the derivative is undefined is because, and by the way, these graphs that I'm drawing are the graph of not the derivative, but the original function f, so I should indicate that. All right, so, but if f prime of c is undefined, it's also possible that it looks more like this, which would be a situation where we actually get a vertical tangent line. So f might look like that, but you still would have a local minimum. Or it's also possible that the original function f is actually undefined itself at that point, so that the derivative is also undefined. So in that case, it could be a lot of different scenarios, but let's say that it's a scenario where we have a vertical tangent line. So the function decreases on one side of the tangent line and then increases on the other. Oops, I drew it wrong. Okay, so in this case, we would not have a relative minimum. But in each of these cases, we would have a local, you'll hear me say local minimum and relative minimum because different textbooks use different terminology. But here you'll have a local minimum. So what you want to look for if you are trying to analyze a function's graph based on its derivative is where you have a change from the derivative being negative to the derivative being positive. You're going to have a local minimum unless the function itself was undefined at that value. Okay, so on our sign chart, we're really not concerned about those points. We're really concerned about the points where the function itself was defined. Okay, how about if we had our first derivative was positive on the left of this x value c, and then it's negative on the right. So the reverse is happening, right? If it happens that at c, the derivative happens to be 0, then it could be, if it's changing from increasing to decreasing, it's going to go through a nice smooth hill shape, right? So at here the derivative is positive because the slope is positive, it's increasing, and here negative slope, and then at the x value c we have a horizontal tangent line. So that's one possibility for the graph of f if the derivative is 0. What if the derivative is undefined at that point? So if f prime of c equals undefined, it could be that it increases and decreases but has a sharp point, right? Or it could be the original function was undefined at that point. So we increase and then we decrease, and there's no relative maximum because the function was undefined. But in all these other three cases, you see how we get a local maximum? As long as the as long as the original function was defined. Okay, so when you see that the signs change, the signs of the derivative change at a particular x value c, you can expect to have local extrema. Now, on the other hand, let's look at part C here. For part C, we have positive slopes on the left and positive slopes on the right. So that means that the function was increasing up till c, then something happened at c, and then it was increasing again. So what might that be describing? Well, if f prime of c is actually equal to 0, then it would look something like it increases and then it just continues. Oop, I did that wrong. Hold on. We want it to flatten out because a slope of 0 means it flattens out. So it's going to increase until it flattens out, and then it's going to start increasing again. So you get a shape like this. You still have a horizontal tangent line. The slope is 0 at this point. Again, this is the graph of f. But there is no relative extrema because it just kept going upward after it flattened out. What if the derivative is undefined? There are several ways that that can happen. But one of them would be if we had a vertical tangent line. So your graph might scoop upward till it's almost vertical and then scoot back downward again. So vertical tangent line, still increasing on both sides of that value c. right? But either way, you're not going to have a peak or a valley. So no local extrema. And of course, if the function's undefined at that point, also no local extrema. So you know for sure, if there's no change in the sign, you know for certain that there's not going to be a local max or min. The same thing for negative on both sides. So this would look like if the first derivative is 0 at c, and it's decreasing, then decreasing, we're going to decrease, then decrease some more with a horizontal tangent line here. That's what f would look like. And if f prime of c were undefined, then it's just going to be this situation where it looks like a vertical tangent line and goes like this. Or maybe the function's undefined at that point. But either way, again, no local extrema. So the only possibility for getting local extrema is when your sign chart shows a change. Negative on the left, positive on the right. Okay. So now we're going to apply this idea. We're going to find the critical values of f. How do you find critical values of f? You look for values where f prime is equal to 0 or undefined. Okay, we're going to determine the intervals on which f is increasing or decreasing. How do you do that? Increasing means f prime of x is greater than 0 or positive. Or decreasing is where the derivative is less than 0 or negative. So the sign of the first derivative is going to tell us whether our slope is positive or negative, which tells us increasing or decreasing. And then we're going to identify any extrema that occurs where we have a change from positive to negative at a point, an x value, where the function is defined. So let's look at part A. We have f of x equals x cubed plus 3x squared minus 9x plus 1. The first thing we have to do is find the critical values. And all that means is find where this has a derivative that's 0 or undefined. So first we must find the derivative. So taking the derivative of x cubed, we get 3x squared. The derivative of 3x squared, bringing the 2 out front to multiply by the 3, we get 6x to the first power, and then minus 9 plus 0. So our first derivative is 3x squared plus 6x minus 9. Notice that both the original function and the new function are polynomials. Polynomials have are never undefined for any x value. Their domain is all real numbers. So we don't have to worry about the undefined, but we do need to figure out where this equals 0. So 0 equals 3x squared plus 6x minus 9. Sorry guys, I need to check on something. Okay, so 0 equals 3x squared plus 6x minus 9 is a quadratic equation. We can use factoring or the quadratic formula. I do notice that all the coefficients have a factor of 3 in common, so let's make our number smaller. So I'm going to divide both sides by 3. So we're going to get 0 equals x squared plus 2x plus 3. And that factors, oh, does it factor? Let's see. Oh, that was a minus 3. Now it'll factor. Okay, that should have been a minus 3. And then it'll factor easily. So 0 equals x plus 3 times x minus 1, right? 3 times negative 1 is negative 3. 3 plus negative 1 is 2. All right, so what we just do from there is set each factor to 0. So either x is -3 or x is 1. These are the places where the first derivative is equal to 0. So what you do next is we want to determine, remember, where f is increasing or decreasing, and that happens to correspond to where the first derivative is positive or negative. These guys are the only places where the sign could change. So what we're going to do is use that to make a sign chart, what we call a first derivative sign chart. So we're representing the first derivative values, y values, on the top and the x values on the bottom. The important x values are the critical values, -3 and 1. Make sure to put them on your sign chart in the right numerical order. And then what we're going to do is we're going to check points in between. We know that the first derivative is 0 if we plug -3 into it or 1 into it. And we want to figure out where we might have positives and negatives on the intervals in between. So the fail-safe way that will work no matter what kind of function you're dealing with is to plug in values. -4 is a value to the left of -3. You could pick -5, you could pick -1,000,000. It doesn't matter. Just test any value to the left of -3. 0 is a good one to test between -3 and 1. And then to the right of the number 1, 2 is a good number to test. All right. So you're going to plug those into your first derivative and see if you get a positive or a negative. So for example, f prime of -4. Now I prefer, when I'm plugging into my first derivative, to have it completely factored. So I'm going to factor out a 3, which leaves x squared plus 2x minus 3. Remember, we know how to factor that. That factors into x plus 3 times x minus 1. So when I plug in to my derivative f prime, instead of having to calculate the exact value that I get by plugging in -4, all I have to do is figure out the sign, right? So plugging into the factored form makes that easier, because look what we would have. We'd have 3 times, and we'd have -4 plus 3. Then we'd have -4 minus 1. This is a positive times a negative times a negative. So I don't actually have to do the arithmetic to know that's going to result in a positive value. So what that tells me is any value to the left of -3 that I plugged in would give me a positive value. And now what if I plugged in 0 to my derivative? Well, that would be 3 times 0 plus 3 times 0 minus 1. That's a positive times a positive times a negative. So that's going to be a negative value. So I know all the values. If I plugged in -2, if I plugged in -0.5, if I plugged in +0.5, any number between -3 and 1 is going to give me a negative result. Okay, and then f prime of 2 is going to be 3 times 2 plus 3 times 2 minus 1. That's positive, 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 which equals positive. So these are all going to be positive values. Okay? All right, so this is my sign chart, and this sign chart will enable me to read all the information off of it that I need. So we were supposed to determine, first of all, the intervals on which f is increasing or decreasing. And I said, well, that's really where the derivative is positive or negative. So what you do is you say, okay, I want f increasing. What intervals does that happen on? Well, that's where we see positives on the first derivative sign chart. So that's going to happen here and here. So what intervals would that be? That first one is everything to the left of -3, so -infinity to -3. Notice I'm putting a parenthesis because it's not positive it doesn't have a positive derivative at -3. 0 is neither positive nor negative. And then where else is it increasing? Well, from the x value 1 up to infinity. To the right out here is infinity, to the left negative infinity. Okay, so where is f decreasing? Well, that's where the first derivative is negative. So that happens between -3 and 1. So we're going to say the interval from -3 to 1 is where the function's decreasing. So in other words, what this function f looks like if we graph it is it's going to go up, and then it's going to go down, and then it's going to go back up again. I mean, this is a very rough sketch, but that's what f basically looks like, and we know that it's changing from increasing to decreasing at these x values. Okay, now, that wasn't all they wanted us to do, though. They not only wanted the intervals where f is increasing or decreasing, but identify any extrema. All right, so I drew this little rough sketch of f. It might be very imprecise, you know, it might be like, ooh, like, I don't know. But anyway, the important thing is, because where the derivative changes from positive to negative or negative to positive, you notice that we have a peak or a valley. So that's where our local extrema will occur. So when it asks where does f have local extrema, we have a local maximum occurring at x equals -3, and we have a local minimum occurring at x equals 1. And that's everything that we were asked to find. Okay, so again, if you have any questions, just type them into the chat bar. But I'm going to move on to another example now, part B. Okay, remember we have 3 things we want to find. Find the critical values, determine the intervals of increasing or decreasing, and identify the extrema. All right, so for part B, we have the function f of x equals 8x minus x squared. All right, so we're going to find our first derivative. The derivative of 8x is 8. The derivative of x squared is 2x. All right, so now we're going to find any critical values. What are critical values? Critical values are where the first derivative is 0 or undefined. This is a polynomial. It's never going to be undefined, so we don't need to worry about that for this example. We just need to find where, for what x values, the derivative equals 0. So we set 8 minus 2x equal to 0. So that means that negative 2x equals negative 8, which means x is equal to 4. So there's only one critical value, one potential place where we have extrema. What do we do with that? Well, we always do the same thing. We draw a sign chart. On the bottom, we have the x values. On the top, we have the function values. You mark off the critical value 4 on your sign chart. And since that was where the derivative is 0, you put a 0 above the critical value. All right, then you want to determine where we have positive values and where we have negative values. So you pick test points on either side of 4. 0 is an easy one to the left of 4, so I'm going to use 0. And then I'm going to use 5. But you can pick any values you want. By the way, the reason I'm putting them in parentheses is I know that at home you might not have 2 different colors to distinguish the test points from the critical values. So at least if you put them in parentheses, then you won't get them confused, right? So these are in the parentheses, these are just test points right? And the 4 here is a critical value. The 4 is going to be where the endpoint of our intervals when we answer questions. You don't want to get it confused with the 0 and the 5. Okay, so let's go ahead and figure out what would f prime of 0 be. 8 minus 2x, so we're going to have 8 minus 2 times 0, which is definitely a positive value. So we're going to have all positive values on the left. And f prime of 5 would be 8 minus 2 times 5. 8 minus 10 is a negative value. So these are all going to be negative values. Okay, so we were first asked to identify where we might have increasing intervals. So where is f increasing? Well, that happens where the first derivative is positive. So looking up at our sign chart, we read that information off of it. Where do we have positives? On the interval from negative infinity to 4. Negative infinity to 4 is where f is increasing. And f is decreasing where we have negative values. Where do we have negative values? To the right of 4. So that would be the interval from 4 to infinity. All right, so just to visualize what this graph looks like, it increases up till 4 and then decreases after that. So the reason why I'm sketching that is because in the next part of the question, they want us to identify any extrema. And what kind of extrema would occur here? That would be a local max, right? So we're going to have a local maximum where the function changes from increasing to decreasing. In other words, where the derivative changes from positive to negative, which is at x equals 4. And by the way, looking at that shape there, you might notice it appears to be a parabola, which makes, oops, I don't know why I erased that, which makes sense because look back at the original function. F of x equals 8x minus x squared. And what kind of a function is that? That's a parabola, and it's one that opens downward because the coefficient of x squared is negative. Taylor's asking, are we going to need to be able to make the graphs? So the answer to that is yes. Ultimately, we will be needing to graph some functions. But at this moment, the reason I'm really sketching it is just to help you visualize what's happening. You can conclude just from the sign chart that you have a local maximum at 4 because it changes from positive to negative. Anywhere you have a change from positive to negative will give you a local max. Anywhere you have a change from negative to positive would be a local min. Personally, I'm a very visual person, so I like to say, okay, increasing means going up, decreasing means going down. Oh, that means I must have a hill, so that's going to be a maximum. So that's how I think through the problem. But do you actually have to draw the graph? No, we were not asked to graph it. In the problems, we were asked to find critical values, intervals of increasing, decreasing, and extrema. On problems where we want you to graph, you'll be told specifically to graph. Okay, so I hope that answers your question. All right, so we've done 2 problems where we had to find extrema. Let's look at part C now. Same instructions. Okay, first we're going to find any critical values. So that means finding the first derivative and setting it equal to 0 or undefined. The first derivative of this function, well, the derivative of 1 is just 0. The derivative of x cubed is 3x squared. So that's never going to be undefined because it doesn't have a denominator, a square root, or a natural log. But it could be equal to 0. So let's set it equal to 0. Now the only way that can equal 0 is if x happens to equal 0. So that's the only critical value. So we're going to make a sign chart. Remember, it's x values on the bottom, first derivative values on the top. The x value, that's a critical value, is 0. It gave us a derivative of 0. And now we're going to test points on either side of 0. So maybe I plug in -1 and 1, for example. What am I plugging into? I'm plugging into this guy. Notice though, whatever x value I plug in, I'm going to get a positive value because I'm going to square it. So I'm going to end up with positives on both sides this time. F prime of -1 is +3, and f prime of 1 is +3. All right, so let's answer the question, where is f increasing? So f is increasing wherever the first derivative is positive. So that's going to be from -infinity up till the x value 0, and then again from 0 to infinity. If you wrote -infinity to infinity, I would not object to that. But most likely in my math lab, it's going to want you to separate it, but I'm not sure. So be aware of that. Where is f decreasing? Where is the first derivative negative? Nowhere. That never happens. Okay. And then where do we have local extrema is the next question. So local extrema will only occur when a function changes from increasing to decreasing, where the derivative, in other words, changes from positive to negative or negative to positive, which doesn't happen. So there are no local extrema. Okay, that's not to say something important doesn't happen when x is 0. There is something significant there, which is a horizontal tangent line. And we'll also talk about something called concavity, and that's important as well. But no local extrema, no max, no min, no peak, no valley actually occurs at that point. Okay, let's look at one that has a natural log in it. So we'll see what happens with this. So first thing is we're going to, since this is not a polynomial function, so it has a restriction on its domain, you should really make a note of that. So since it has a natural log in it, remember we're only considering x values greater than 0. It's easy to forget that and make come to some incorrect conclusions. So just remember, natural log, you can only take the natural log of positive numbers. All right, so let's find the first derivative then. So it's going to be 8 times the derivative of natural log of x is 1 over x. That's a fact you need to memorize. Minus the derivative of x squared is 2x. So our first derivative could be thought of as 8 over x minus 2x. Okay, now we're interested in where this either equals 0 or is undefined. I can very quickly see where it's going to be undefined. When x is equal to 0, we would have division by 0, which is undefined. But keep in mind, x isn't allowed to be 0 anyway, because 0 is not in the domain of the natural logarithm. It's undefined if you plug it into the original function. But still, let's just make a note. So f prime of 0 is undefined, but 0 is not in the domain of f, which I'm going to denote f with a little. Actually, take that back. I prefer it the other way around. The domain of f. Okay? All right. So just keep that in mind. And then we're going to check where f prime of x is actually equal to 0. So that would be 8 over x minus 2x. equals 0. And so this is a rational equation, and I think it would be helpful to clear the denominator of x. So what I'm going to do is multiply both sides by x. And so distributing the x, we would get 8 minus 2x squared equals 0. All right, the way we would solve that, well, you have a couple of different options. I'm just going to subtract the 8 over, so we have negative 2x squared equals negative 8. And then that would mean x squared is equal to 4 if you divide by negative 2. And by the square root property, that would mean x is plus or minus the square root of 4 or plus or minus 2. So we actually have two really valid critical values, but we're also going to mark the one that's not technically a critical value because it's where the function's undefined. I'm going to put 0. Oh, actually, I take that back. We don't have two critical values, and we only have one. Because here's 0, here's negative 2, and here's 2. But remember, x is only allowed to be positive. So let's make a little, I like to make a little squiggly there. And just remind myself, none of these are in the domain. So we're not going to use any of those values. We're only going to focus on things to the right of 0. So 2 is really the only critical value. Because remember, critical values are where the derivative is 0 or undefined, but the function is defined. I do want to mark this is the first derivative sine graph. You want to do that because we can also have second derivative sine graphs. And x values are on the bottom. And now we're going to check values in between. So between 0 and 2, we could check the value 1. After 2, we could check 3. Remember, we're plugging this into the first derivative, which was 8 over x minus 2x. So f prime of 1 would be 8 over 1 minus 2 times 1, which is definitely a positive value. And f prime of 3 is going to be 8 over 3 minus 2 times 3. Let's see, that's going to be 2 2/3 minus 6. So that's going to be a negative value. So we have positives, negatives. And at 2, it turned out to be 0. All right, so we have completed our sign chart. We've identified our only critical value, which is 2. And now we need to identify intervals where f is increasing or decreasing. All right, so f is increasing on the interval from 0 to 2. And f is decreasing on the interval from 2 to infinity, right? Because increasing where the first derivative is positive, decreasing where the first derivative is negative. Okay. And then the last thing is we need to know where we have a any local extrema. So do we have any local extrema here? Well, remember, increasing and then decreasing looks like this, right? So we have a hill. So it looks like we do have a local maximum at x equals 2. Okay, remember you can type any questions into the chat bar, so just feel free to let me know before we stop if you have any questions, because that was the last example. Okay, so this is called the first derivative test for local extrema, where you draw a first derivative sign chart, and wherever you have a change from plus to minus or minus to plus, then you come to the conclusion that you must have a local max or min. Yes, Karina, the reason that x must be greater than 0 is because the original function involves a natural log, and you cannot take the natural log of 0, and you cannot take the natural log of a negative. Good question. Any other questions? Okay, so I just want to remind everyone, first of all, if you could give the video a thumbs up if it was helpful, then that helps other students to find the video. Also, just want to remind you that in D2L, if I can find it, there we go. In D2L, remember on the right here, we have moved into the test 3 topics, graphing and optimization. We've just discussed our first topic of optimization. Optimization means finding maximums and minimums. We just looked at section 4.1. We did the in-class notes, but there's also some home notes. So I'm going to open this up and just remind you, you should be looking at these as you go along. Okay, and the solutions to the home notes are there if you click one step over from there. And also there's videos, there's all kinds of good stuff in here. So I think the best thing is as soon as possible after the actual lecture to go in and work through the home notes before you forget what we talked about. I've seen a research study where they showed where students who reviewed their lecture notes within 24 hours after, preferably within a couple hours, but within 24 hours after the class lecture, retained something like 80% more of the information. It was a drastic amount. So before you forget what we talked about, go ahead and look at the home notes, which is like a activity in a way. You try to work through as much of it as you can by yourself, and then as you find that you don't know, then you go ahead and look at either the written out solution, which is on the next page, or also as you go along there's videos you can click on. Okay, and then of course don't hesitate to send me your Ask My Instructor questions. Remember that although we only meet once a week, that I'm available to help you throughout the week. So everybody have a good week and don't be a stranger. Bye guys.